vibration acceleration. Okay, so the principle used by these sensors is that if you have a mass which is attached to the vibrating object through a spring mass system, then the mass will vibrate, and that vibration of you can measure the vibration of the mass by using a displacement sensor, and that displacement is somehow related to the object displacement. Okay, so there is some theory about how a mass attached to a spring behaves in order to come up with the right expression. So we can use this device in two setups. One is to measure the acceleration, which is the rate of change of, so if xi is the position of the vibrating object, the second derivative of xi is the acceleration. If you want to measure just the vibration, it will be the displacement of the object. Okay, so an example of vibrometer would be a seismograph for you to measure the movement of the earth, and an accelerometer, they exist all the way. Your phone, an iPhone would have an accelerometer in it. However, I don't think they use something like this. So in order to derive an expression which shows how the acceleration of the object is related to the displacement on the scale, let's call that actually XO. It's actually XR, which is XO minus XI. XO minus XI being the difference in the absolute motion of the mass and the object is the relative displacement, and that is actually measured by the displacement sensor. So for that, we need to use something you need to use a free body diagram. So the free body diagram of the mass. This is showing the spring, this is showing the damping force. And then we need to use Newton's laws, which says that the external force is mass times acceleration. So we have the spring, the damping term, the spring term equals mx double dot. Now, one thing you'll note is that mg is not in this expression. The reason why mg is not in this expression is that initially mg balances against kx. So the spring constant, then that gives the spring an equilibrium displacement. So let's call that equilibrium. And so it actually does not figure out in the equations because of that. Okay, so this is an expression for the net force. We can now write the relative motion of the mass with respect to the object. So it'll be XO minus XI, which is XR. So XI is XO minus XI. And what we can do here is we can write the same thing as XO equals XR plus I. In other words, I'm trying to eliminate X0 or the motion of the object. Remember, the XI is the motion of the object which we need to measure, and XO is that of the mass, which is in the setup. Okay, so here I'm replacing XO with XR plus XI, and so this expression will have now only XR, and there will be an XI left over. So this is the simplified expression for the displacement only in terms of XR, XI, and constants. And we are trying to estimate this because that's the displacement of the object. And this is measured because we have a scale there. Now we do some simplification, very standard in vibrations. There's a natural frequency, which is square root k divided by m. There's a damping constant, which is b divided by 2 square root km. So we can eliminate k and b. So k and b disappear, and we get this expression. I think there's an error here. I think this should be omega n squared, not k. Okay, so here's the expression for the motion of the relative displacement. It depends on the acceleration of the vibrating object. Now let's assume that the vibrating object has a sinusoidal profile. Okay, then if you substitute xi and then take the second derivative and then solve for xr, you will get an expression which looks like this. It'll have some amplitude, which is unknown. We have to find that. And there'll be a phase difference. So there's a phase difference between xi and xr. We can actually solve for phi and xi. This is like a standard exercise when you do a course in numerical methods where they tell you how to solve this. So turns out that there's an analytical expression which tells you what the ratio is as a function of R and psi. So R is omega divided by omega n. And then there's an expression for the phase. It also depends on R and psi. Here, R is omega divided by omega n, and psi I had written down earlier. Here. Now, that's something which is there in sort of textbooks. You can read about it, but this is how the actual measurement is done. And it's kind of, I think it's very interesting. Let's say we want to use this as an accelerometer. So what we're interested in is, remember that xi was capital Xi sine omega t. So we can differentiate this twice to get an expression which looks like this. And I think you can, this should not be there. So once you differentiate, this is the amplitude which we're interested in measuring. So what I do here is I rewrite this expression. I take this expression, xr divided by xi is something related to r square, where r is omega divided by omega n, and rewrite it. So when I write it, I have, this is r, I just expanded it, and I just kept the r as it is. So that came from the previous page. So now what I can do is I can write xi omega squared divided by xr omega n squared, that's moved to the left side, is just going to be this thing which depends on r and psi. Okay, let's call this as 1 divided by HA. What I'm going to do next is plot. I'm going to plot HA, note that it is a function of R and psi, as a function of R and for various psis. So this is a one-dimensional, two-dimensional plot involving HA as a function of R, but then there's a third variable called psi, which, so what I do is I plot this for different psis. Now, what I'm going to do is I'm going to choose. So what is HA? HA is basically depends on R and psi, but R depends on omega n, and psi depends on, these things depend on B and K, spring constant and damping. Right? So I can choose whatever I want B and K to be because I make the whole system setup. So what I can do is I can choose B and K such that HA is in this range. HA is close to 1. You can see that happens when R, this is R, is less than 1. So this is 1. And so here, this is less than 1, much less than 1. Here it is 1. And then I can also choose such that psi is 0.707 because you can see that 0.707 seems to be the one which is staying almost close to being 1 for the longest possible R. Right? This one deviates, this one also deviates, but this one stays 1 for a fairly large time. So what I do is I choose HA to be 1, which means that omega will be, R is, okay, so when HA becomes 1, is that? It actually boils down to, it's right here, sorry. Okay, so when HA is close to 1, as I said, omega divided by omega n is close to, is much less than 1. So if omega divided by omega n is much less than 1, that means omega n is large. If you can make this less than 1 by making omega n much, much larger than omega. But what is omega n? It's k square root k divided by m. So if you want a large omega h, you want to choose a large k, small m. So choose k relatively large for m. Because m is small, the accelerator can be kept small. So it can be very small, it can fit in your phone. Okay. Once we have done that, remember that this was HA when we tried to make this close to 1 by choosing a large, small mass and large spin constant. So this ratio is 1. That's what I wrote down here. So now if you want to measure this is the acceleration of the object. So the acceleration of the object is this. It's simply given by xr times omega n squared. Omega n is something related to the natural frequency of the system, something which we have designed. XR is measured. Go back. There was a scale, and this scale measured XR. So XR is measured. Omega n is a constant from design, and so you can everything on the right side is known, and you can estimate the acceleration. That's how an accelerometer works. Now we have to also use the vibrometer. So for vibrometer, we look at the same ratio again, but now we call this whole thing as our HD. We can make a plot of HD as a function of R for various psi, just like before. So this is what the plot looks like. We zoom in on the place where HD is close to 1. That happens to be when omega divided by omega n is greater than 1. So R is much greater than 1 in this range because it's 1. Omega divided by omega n is much greater than 1, which means that omega n should be small. By making omega n small, you get R much greater than 1. We also see that if you choose psi as 0.707, you get the biggest range over which HD is equal to 1. So our key design points are we want psi to be 0.707 and we want omega n should be small. So this basically determines the damping, but if you want to determine K and M, you need to use this expression. So we choose a small K and a large M. Making M large will make omega n small. So as M is large, the vibrometer tends to be big. Okay, and this is good news because vibrometers measure basically, for example, a seismograph measures the displacement of the Earth, and so you really don't want to travel with something as big as that. So it's fine if that was a large value. So you can make the seismograph as big as possible, no problem, because it's going to be stationary on the Earth. So once you do that, this was tried to make close to 1. So XR divided by XI is HD, which is 1 now by design. And so if you want to measure the displacement of the object, all you do is measure the displacement of the small mass, or sorry, the big mass. So you just need to measure XR, and that gives you the displacement of XI.